either your email or also in Telegram or also in WhatsApp. So please make sure to be tuned, stay tuned. All right, so starting for today's level 1 track, it's going to be about an example use case for MeTTa and using it as a graph traversing algorithm. So yeah, so I'm going to show you a little bit of a use case on how you can utilize MeTTa for pathfinding algorithm. We'll start with a general description of how the algorithm is supposed to work on a graph database from a higher level. And once we have a general understanding, then we can go ahead and look at how that implementation is going to be done within MeTTa itself. And after that, I would like you guys to try it out on your own after this call so that you can actually get the hang of like how things work with this kind of algorithms. These kind of use cases and problems that we are showing you guys, for those of you who've been following the level 1 track, they're inspired by the problems that you're going to be facing during the hackathon time. So we really want you to take them seriously if you want to be participating in the hackathon, because they're going to give you a serious advantage over winning the hackathon itself. All right, so without further ado, let me quickly share my screen and we can start straight.
Hey, everybody, this is Nefertiti. I just wanted to say while you're setting up your screen, Yee, thank you for joining. This is yet another opportunity for you guys to learn and to also advance yourselves for the hackathon. When you join us on Friday, we'll have a lot more information about those prizes, about where the hackathons will take place, what you'll need to do to participate. So if you participated again, you go back to your GitHubs. I think that if you've built something using MeTTa, if you have a team that you've worked with before, rekindle with that team. Look and see what that project looks like, what the project looks like. And if it's something that you think is worth building, utilizing Omega or any other tools, I would suggest that you think about that. So just wanted to give you guys a shout out, let you know that we will be giving out a surprise on Friday and more information on Friday. So thanks again for joining, and Yves, I'll let you take it back from there. Thank you.
All right, thanks for that, Nefertiti. All right, let me quickly share my screen. Okay. Can everyone see the slides? You can just give me a thumbs up anyway. Just making sure. All right, cool. All right. So today, what I'm planning to cover is basically what this algorithm would look like when implemented in MeTTa. So the algorithm is going to be a BFS, breadth first search over graph. So I'm pretty sure most of you might be familiar with this algorithm, but if you're not, this slide is going to make sure that you're all on the same page before I can start. So basically, what the algorithm is trying to do is find the shortest path on a graph. So when we say the shortest path, it can mean anything. It can mean the shortest number of steps of doing something. It can mean the shortest or the closest connection between multiple people. It can mean the shortest path between two different points on a graph, meaning on a road. It could be a road. It could be like Google Maps road. It could be flight optimization. So it could be, in that case, it would be meaning the shortest number of flights you need to take from point A to point B. And yeah, there are a lot of different applications for this use case. So that application is going to be determined by you guys, but we're going to go and look at one of the possible applications which I'm trying to demonstrate here. So the application I have in mind is basically what's the smallest number of flights or layovers you can take in order to reach from a given city to another one In this specific case, we're actually interested in reaching to Istanbul. Addis Ababa, for those of you who don't know, is the capital city of Ethiopia. Istanbul is the capital city of Turkey. So basically what we want to do is we're starting here from Addis Ababa and we want to reach to Istanbul. So we're trying to figure out what's the shortest number of flights we can use in order to reach to Istanbul, because we don't have a direct flight from Addis Ababa to Istanbul. It's just a hypothetical scenario. So this kind of algorithm, this kind of breadth first algorithm, is the purpose of it is basically to find us this shortest path. And the way it does it is basically starting from our starting point and exploring our graph until it finds our goal, our destination, or our goal. That destination is going to be the place we want to go, but then along the way, it's also going to keep in mind the number of steps or different detours we had to take in order to reach there. Let's actually see how this might look like. So before we start into the algorithm, there are a few words that you might find interesting. So the first is going to be a node. So a node is basically a point on a graph. It could be any of your any of the structures or the destinations or any of the things that you're interested in. So in this case, it's actually a city, but if your use case is going to be, for example, what's the shortest or what's the closest connection to a given person, that node is going to be the name of the person or the name of different people. If your use case is finding the shortest possible number of steps to perform a given task, then in that case, those nodes are going to be the number of tasks or like the step sequences that you are going to be performing. So in this case, a node is a city, and one example is an Addis Ababa. And the next one is an age. So this age is basically a directional connection between different nodes. So that directional connection is going to be very useful because sometimes you don't want connection to be bidirectional. For example, if you see the use cases of a people, then one person might know another person, but that other person might not be knowing. If person A knows person B, that doesn't necessarily mean person B also knows person A in case person B is famous. So these kinds of relationships are going to be encoded with an age. So an age is basically a connection. The city is we have. Then we have Istanbul here. Istanbul is also another node. The interconnection between these nodes, for example, between Cairo and between Istanbul, that's going to be an age. So we have an age between Cairo and Istanbul. This age indicates that there is a flight between those two. So what's terminating. So something other than this, what we might be interested in is a neighbor. Well, this is kind of like intuitive. A neighbor is basically like the closest connection of a node or a direct connection of a node. For example, if you have the node Addis Ababa, if you take a look at the node Addis Ababa here, then its neighbors are going to be Dubai and Cairo, and also Frankfurt, because they're all one node away, one connection away from the given node Addis Ababa. So this is what we mean by neighbor. If you take, for example, Paris, then Paris has two neighbors, London and Frankfurt, because those are the only nodes you can reach by a direct connection. So that's what we mean by a neighbor. A distance is basically the number of steps you have to take in order to reach a given node. For example, if we start from Addis Ababa here, then if I need to go to Dubai, I can do it with a one number of steps or one flight in this case. If I'm planning to reach from Addis Ababa to Paris, then I might start from Addis, then take one flight to Frankfurt, then take one flight to Paris. So yeah, that's basically what we mean by this one. All right. So after distance, what we want to consider is routes. So a route is basically just an aggregate of like the steps we took in order to reach a given point. So if you started from Addis Ababa, for example, then if we wanted to go to the park, for example, the previous example, then what is the route in order to reach here? We don't only want to keep track of distance, right? We also want to keep track of the route, because without the route, the distance is going to be useless for us if we want to go there. So basically, starting from Addis, we go to Frankfurt, we go to Paris. This is one route. In case there is another route with multiple distance, we can also take a look at that. We can go to Cairo, then from Cairo, we can go to London. From London, we can also go back to Paris. But in this case, this route is a bit longer because we're taking three steps, or we're taking a journey of a distance of 3, as opposed to when we start from Addis Ababa to Frankfurt to Paris, it's going to be 2 distance, or 2 number of steps. So yeah, that's what we meant by route. These terminologies are just to make sure everybody's on the same page so that we don't get confused when we get into codes and terminologies. All right, so I'm actually trying to cover a lot of ground here, so that's why I'm a bit fast-paced. So, but in case anyone has a question, please feel free to raise your hand and interrupt me, and I can explain it to you then. All right, so moving on to the next slide, this is going to be what our algorithm looks like. So for the breadth first algorithm, we kind of modified it a bit so that it kind of looks a bit similar to our MeTTa implementation. But the main idea is essentially, as I said earlier, just trying to find the shortest path. And until it finds our destination, it's not going to be, I'm sorry, it won't stop until it finds our destination, is what I meant. All right. So here, for example, we can start from our shortest. We only need to give it our starting node and our destination node. So if you see here, for example, what we want to start from is Addis Ababa, what we want to reach at is Istanbul. So our start node is Addis Ababa, our destination is going to be Istanbul. Once we have that, we're going to enumerate our distance. Basically, we are going to iterate through our distance until we run into a limit. This limit here is kind of optional, because if you want your search to be terminating at a given maximum cap, then it makes sense to give it a limit. But if you don't want your search to stop, even if it's searching a very long route until it finds its goal, then you can deal with that without this limit at all. But for our case, we introduced a term called limit. It's basically telling it you need to search to find the goal, but I don't want the goal to be farther than 3 distance or 4 distance. What I mean is basically if the goal is more than 4 distance away, I don't want to go at all. So just stop your search is what this terminology is standing for here. So for each distance, we are going to be searching the routes that we have that start from our starting point and that goes until the goal. And this distance is going to be passed here because we want to keep track of how many, we want to keep track of what level of distance we are at the given moment. So if we found a route, then that's what we are doing here. We're going to return the route that we have discovered. So if there is a route that can connect the start to a goal within this distance, so when we start, this distance is going to be 0. So if we have a route that starts from our starting node, reach to the goal given a distance, then we're going to return that route. But if that's not the case, then we're going to continue iterating until we run out of a limit. When we run out of the limit, then we're going to return that we have not discovered any route because we have reached our limit, or maybe the goal didn't decide. So that's basically what the code is trying to do here. And we're going to be stepping over our example later on so that you can get a better grasp of what this algorithm is doing. But the route, what it's doing is keeping track of every node it has visited so far. So this is going to be essential for like returning a path from a starting node to an ending goal, because that path is actually what we are interested in the end. So we keep that in a list of collection. We search from the start until we reach to the goal. So here we have routes so far, which will contain only the starting node in the beginning. We have the city we're at. We have the goal where we want to reach, and we have the limit here. So if we're only searching at the distance of one, then we don't want to be searching more than one distance of one, because in the next iteration, that distance is going to be incremented. This this is going to be helpful because we want to start from the shortest route first. So if we found a path that can connect us to the goal at a distance of one, for example, or even at a distance of zero, if we are already at the starting goal, if we're already at the goal, then at distance zero, we might find a route without doing anything that can lead us to the goal. But if we're not there yet, we can keep incrementing the distance until we run into our limit so that we can find the shortest distance or the shortest route first before the longest path, because there could be multiple paths. So that's why we're passing the distance here. So as I said earlier, if we are already at the goal, we want to return the route so far. But if that's not the case, we check if we have any remaining edges. If that's the case, then we abandon the hits entirely, and we're going to be returning what we have. If none of the above is true, we're going to search for each neighbors of the city, and if n, or meaning the neighbor, is not already on the route, we're going to add it to the route by using this code. This is just a pseudocode, so don't mind the syntax here. What we're basically saying is, if we found a neighbor in the city, but that neighbor has not already been visited so far, that's why we're checking here. If n is not already on route so far, then we're going to recursively search for the remaining goal by decrementing the edge left, because we want to stop our iteration whenever we reach our distance limit. But we also want to update our start node, because earlier it was just a city, but now we have updated it to the new city, which is n here, which is the neighbor of the previous city. Then we also pass the goal unchanged because that's our final destination. So if we keep iterating, then eventually what we're going to reach is either the goal, because this is one of our base cases. If you remember, on a recursion, we have base cases that is helpful to terminate the recursion. So this is one of the base cases. Another base case is when we have no remaining edge left. That's going to also terminate the recursion. But if neither of the two is true, we're going to iterate over all of the neighbors of the city until we reach at the goal, or until we reach at one of the base cases. So this piece of code right here is not going to be returning only one value, it's going to be returning multiple value for each of the neighbors here. So this will be much clearer when I walk you through the actual execution on the graph. So right here, this is an example run. As I told you earlier, our start node is Addis Ababa. What we want to end up in is Istanbul. So the first execution is going to start from Addis Ababa as usual. So when we step our algorithm one more time, what we reach at is three different explorations. Because remember, if you reach here, if the city is the goal, it's the first thing that we check. The city is not the goal because our goal is Istanbul. And we also check if we have any remaining edges left. This is just the start of the algorithm, so we will have some remaining edges left. Then what we are going to explore is for each neighbor of the city we started at, we wanted to recursively search for routes starting at that neighbor. So that's what these broken lines you observe right here are denoting. So the neighbors of the city Addis Ababa are Cairo, Frankfurt, and Dubai. So we have direct connection from Addis Ababa to this destination city. So once we reach there, then we're going to sequentially check if we are at the goal for each neighbor. So on the next call, we're going to check, well, is Cairo actually the goal? So that means we are going to be recursively inside routes. And after we reach inside routes, we have a city. And if we check if the city is the goal, but remember, the city has changed. The city is now Cairo instead of Addis Ababa. So we check if Cairo is the goal, but it's not the goal, so we don't stop our iteration yet. We check if we have any edges left. Let's see, we are searching at distance 1 because this is going to be the closest distance we can find our nodes at. So distance 1, we started at distance 1, so by the time we reach at Cairo, that is going to be distance 0. So we have no more attempts left, so the recursion is going to stop. The same thing is going to be happening for Frankfurt and Dubai because none of them are the goal, and you're only searching at distance 1, so we have not found our destination yet. So the next is going to be incrementing our distance and trying to search at distance 2. So when searching at distance 2, we're going to start from the same place. We're going to start from Addis, then we went to Cairo, but now we have an additional distance we can search for. So we are exploring the neighbors of Cairo too. So when we search for the neighbors of Cairo, we discover 2 more cities. One of them is London, the other one is Istanbul. But when we check for London, London is not our end goal. And by the time we reached at London, we have already executed like 2 distances, and our limit is already 2 distance. So we stop our iteration and we return, just like our algorithm. We are not at the goal. We are also don't have any more edges left, any more remaining distances left for us to explore, to keep exploring the graph. So we stop our execution at London. That's why it's saying the execution here is abandoned. Then we go to the next neighbor, which is Istanbul, and which is something which is actually the one we are looking for. It is our goal. So then in this case, we're going to check if the city is the goal, and it is the goal. So we return the route so far. What is the route so far? It's the path we took to reach here. That is from Addis, we went to Cairo. From Cairo, we went to Istanbul. Then this is going to be the route. So Addis, Cairo, Istanbul is our one route. But we don't necessarily have to stop here. We can keep exploring because we remember we also have the Dubai as a neighborhood because Cairo was not the only neighbor of Addis Ababa. So if you saw here for the first call, we had more than 1 neighbors. That was Cairo, the first one we explored, but now we're also going to be exploring Dubai. So starting from Dubai, the same path, we're going to look at the neighbors of Dubai. The first one is London. Second one is Istanbul. London is abandoned for the same reason because it's not the end goal, and we also don't have any more remaining distances we can cover with. So we start iterating on London. But then when we look at Istanbul, then that's actually our end goal. So we keep Istanbul. We found another path. So now we have 2 paths that we have discovered. The first one is Addis Ababa, Cairo, Istanbul. The second one is Addis Ababa, Dubai, Istanbul. So we have 2 paths that are both at distance 2. And since we want to return only the shortest distance, we're going to be returning these 2 paths alone. We are not going to increment the distance and search for more paths because we have already found the shortest possible that we can discover. But if we have not discovered the goal by the time we reach here, then in that case, we will actually keep iterating for the next path. All right. So this is actually how the general execution works. So, well, one more path actually you might be able to discover is, well, one of the other direct neighbors is Frankfurt. For the same reason, we abandoned Paris and Europe because they are distance 2, but we keep Istanbul, so we have found a third alternative for us to go at the same distance. So we have multiple options here. So yeah, these are the 3 shortest paths that we have discovered. All right. So in order to write it in MeTTa, we will need different components I showed you so far. We're going to look at them step by step. And I don't think we'll have time to run everything, but you guys can try them out on your own and ask any questions in the help desk as well as on our next session. So yeah, any questions from you guys so far? All right, feel free to interrupt me if you have any questions. Let me quickly switch my screen and open the presentation. All right, so this is a small example code I have been trying to write. So you can go over this example. There are also going to be some comments in there to help you understand how the algorithm is actually going to be working. But for the sake of time, I'm going to start directly from the BFS implementation. I will be sharing this code with you guys later on. So let's go ahead and start from our shortest route algorithm, because this is what we are actually interested in. So in the shortest route algorithm, to make things more visible for you guys, just go down a little bit. All right, so in the shortest route, just like our pseudo code earlier, we have our start city and we have our destination city, the starting point and the goal of our search. So here we added one additional check because practically speaking, sometimes you encounter cities that don't really lead anywhere. So we want to check if the start city doesn't have any connections or if the destination city doesn't have any connections, because if neither of those have any neighbors, then it's practically impossible to reach them by any means, basically. So this if stranded function is a very simple match query that's going to be searching for our graph representation in order to find a neighboring city for the questionable city in the city in mind, the city we have in mind. And before I go deeper, I think it's only fair if I show you what our presentation actually looks like. So here you have we have different information, flight information, and also other types of information, basically to check or to store the different types of connections between the graphs. So just like I showed you earlier on the slides that we can connect multiple nodes, here we have an edge called flight, and we have connection between Addis Ababa and Nairobi. So this flight is basically the name of the edge we have decided to use, but it doesn't really matter. But the main connection we're interested in is the Addis Ababa between Nairobi connection. All right, so once we have that, we're also going to be listing multiple direct flights like so. We have all these direct flights from Addis Ababa. We have to Nairobi, Cairo, Dubai, Frankfurt, Mumbai, and so on. The same, we define the same thing from Nairobi. Starting from Nairobi, we have a flight to Johannesburg, we have to Dubai, and so on. Same goes for all of the cities you see over here. This is just the graph representation we are interested in. And not only there is a flight edge, we also have a railway edge, which connects multiple cities. So in our case, for our graphs, we don't really care how we get to a given city. For example, in that case, it makes sense to have multiple railway and flights, multiple edges like railway and flight. So yeah, that's one more information. Another is simply kind of like an annotated information because we don't really use it for this graph traversal, is this country edge. So it's basically assigning a country for each of the cities. We don't really use it a lot, but sometimes you might be interested in storing multiple properties for a given node, which becomes handy. For example, you might be representing the cost of going to Addis Ababa, like so. If you have an edge called costs, then from Addis to anywhere, you might say, oh, it costs like 10 hours or something. Or you might store something more complex, like so, from Addis, flights from Addis, like from Addis to Nairobi, for example, it might cost, might say 2.5 hours. These could be like additional attributes you might be interested in storing in your graph. But in this case, we're only storing the country of the given city, and we're not really going to be using it for anything, just here for revision purposes. All right. So once we have this, then what we can continue to is our traversal. Let me get back to our its stranded function here. It actually used to be a link like so. It's going to be a variable. We want to search for any kind of connection within this match query. I'm sure you guys are aware of what this match query can do by now. So we're searching for any kind of link. It could be a flight, it can be a railway between the city in question. This city is going to be if the city in question is Addis Ababa here, then our match query is going to be representing Addis Ababa here. So this is going to be how the match query is going to be constructed in real time, but this neighbor city and these links are going to be determined by the matching query itself. We don't really care. We just want to make sure there is a link connecting Addis Ababa to any kind of neighboring city. Then if there is a neighboring city, we want to return that neighboring city, and we want to collapse everything into a single expression. So this collapse, if you guys have forgotten probably, what we are trying to do with collapse is basically collect all of the results of a match query into a single list. So sometimes match query might return something empty, and you might see it as these square brackets in your terminal. And we don't really want that in our execution because that's very hard to handle. What we want is an empty list. So this empty list is more deterministically handleable. I mean, in another word, it's easy to handle for you algorithm. So that's why we collapse it and check if there is actually nothing found by the search in that. If we found nothing by that space search, we're going to be returning true or false based on that information. So here we have an equality check. If this is equal to empty, then that means the city we're searching for is stranded and we have really no connection to that city. But if that's not true, then we will be returning false because we have actually found some kind of connection. So for this case, we're going to be returning a lot of information. It could be Nairobi. If you go back up, you can find multiple connections that start from ID. So you can say, well, all these cities are actually places you can actually reach from ID. So that's going to be returned by our match query server. So we can return that by our match query. Right. So you get the idea. I'm going to make it easily understandable for you guys. Yeah. Basically, we just get the list of all of the cities that are reachable from ID. And as you can clearly see, that is not equal to an integer. So this is going to be returning is stranded as false. So if, however, either of the cities, either the start city or the end city is stranded, then we are going to be returning no routes, meaning we couldn't find any distance, any path between the two links. That's what we're going to be returning. But if that's not the case, we can actually start our search at a given depth. So here, for our search, we're giving it start depth of 0 because we're not really starting like literally the easier representation of the for loop because we want to start our search at distance 0, but we want to keep our search at a maximum distance of 5. So that is the parameter, that's the whole purpose of the parameter here. But since we don't really have a for loop in MeTTa, we're going to be using a recursive function like so. So as you can see, we start from a start city, we start from a destination of our city, current depth and max depth. We can have Addis as a start city and Istanbul as an end city. Wait, I'm checking, we have Istanbul here. Oh, yes, we have Istanbul. Cool. So we can start like this, and then we can start our current depth at 0, and our maximum depth is actually 5 in this case. So this is our starting execution of the algorithm. So what is this doing? So right at the start, we have our base case here. So we also have two base cases here. It might be a bit subtler to find. It is checking for maximum distance or maximum depth in this case. It doesn't really matter how you frame it. One of the base cases is stored here. Another base case is actually somewhere here. So here you can see that we are returning our found routes. So the routes that we have discovered so far, we're returning them. That's also a second base case. So this is routes found. Routes found. And if we found no routes so far, then we're going to keep recursing until we hit our depth limits. So now let's walk over this recursion step by step. So when we start, our current depth is 0, our max depth is 5. So when we compare between the current depth and the maximum depth, we're going to find nothing. It's not going to be true because our current depth is clearly smaller than our smaller than our maximum depth. But here we're checking if the current depth is actually greater than maximum depth. So this way of representation, I hope you guys are familiar with this by now. MeTTa uses like a prefix notation. So we put the operator in the beginning of the function call, no matter what operator we're using. But in another language, this will be the equivalent of basically putting the greater than symbol right here. So we're basically checking if the current depth is greater than the maximum depth. But clearly in this case, that's not true. So we're going to be jumping over this representation and we're going to go to the else case of our if function. So inside the else case, what we're doing is we're trying to get every route that starts from our starting city. This is going to be the start of our route list, the same representation like the pseudocode algorithm I showed you guys earlier. And we start from our start city, we go to the destination, and we give it the current depth. And currently we're at 0, right? Remember, so we're at 0. So we're going to search if there is any distance, any goal at that given distance or at that given depth. So let's go to the get routes function and see what that looks like. In the get routes function, look what we called it with. We called it with the start city. The start city is going to be Addis Ababa. That's going to be our start city. The destination is going to be Istanbul. And the remaining depth is actually 0 in this case because we started from empty. And this route so far is actually going to be an already populated list, which is expression of an expression in Addis Ababa. So yes, that's what we started with. I just brought it here, brought it up from here. So when we call this function with these parameters, let me format it a little bit better so you guys can see it clearly. So current city with Addis Ababa, our destination is Istanbul, our remaining depth is 0. Then when we call this function with these parameters, the first check is going to be, are we at the current destination already? And unfortunately, we're not because the current city is Addis and our target is Istanbul, so we're not there. Then the next thing we check is, are we out of depth to search? And unfortunately, in this case, we are. So we're going to call this empty function. So this function might be a little bit new for you guys, but essentially what it's doing is it's telling the function to return nothing. And this is the equivalent in MeTTa. If you're writing Python or if you're writing some other function, you're basically saying, well, I don't want to return anything. If you don't want to return anything, you can make the explicit example. If you're familiar with Python, you can make the explicit and say return none. Or if you're actually writing some other programming, or if you want to make it explicit, you can just leave the function as it is and you return nothing. But in MeTTa, you have to make it always explicit. And this empty function will be responsible for returning nothing because we have not really found anything. So when we reach to the get routes, we're going to return nothing, but we call the collapse function here too. Remember, the collapse function is used to collect the result into a single list. In this case, we have nothing returned, so it's going to be collapsing it into an empty list, which is going to be very easy to handle by any part of our code. So this is going to be checking if our routes we found so far is empty. In another case, if we have not found anything so far. And if we have not found anything so far, what we want to do is continue our search at a greater depth because we have not found anything at the current depth. So that means, that means we're going to increment our current depth by 1. We're going to keep the max depth as it is. We're going to keep the start city and the destination also as it is. We're only incrementing the current depth that we are at the moment. And this is going to be making a recursive call of the same function, but with an increased current depth. So as you can imagine, this path is going to be repeating again and again until either we're going to be reaching a maximum depth of 5 or until we find our actual path. All right, so to make things a little easier or a little understandable, let's go through this one more time. Let's assume we are already, for example, at distance 2 or at depth 2. So the same check is going to be started. Remember, if you are having trouble understanding this code, just try imagining putting the function in the middle of it. And that's going to make things a lot clearer. So we're checking if the current depth is greater than the max depth. So if the current depth is greater than the max depth, then what we're going to do is return because we have already run out of the limit. But in this case, we are not really there because we are still at depth of 2. So this is going to be false. I'm going to return that. Or maybe I should just keep it. But this is going to be false, and we're going to go to the then case of the is function. Inside there, we're going to be calling the getRoute function again with the same configuration of a start city. This is the route from the start city, and we have a start city. It depends the start city we found, but we will use one of the examples from the slides because that's what we're going to be reaching at anyway. We search for the destination. The destination doesn't really change, but we have the current depth right here. So yeah. So just give me a minute. All right. So if you remember earlier, where can we reach from Addis Ababa? Because if we can't find any direct goals, we're going to be searching at its neighbors. So why are we going to look at its neighbors? We're going to look for, all right, let's see what our graph looks like. So where can we reach to Istanbul? Yeah, let's search for Cairo first. I'm just skipping through some steps here so that because of time you can understand things a little bit better. So yeah, where were we? So in this case, our start city is going to be the same, of course, but our yeah, actually, our start city is going to be Cairo because remember we changed our neighbor in order to find a better destination for our given searching parameter. So now, after going through some steps, we've already reached at Cairo. All right, so let's search after we've reached at Cairo. So this getRoutes function call is going to be changed. All right, so let's make the distance current depth at depth 1 because Cairo is one step after traversing from our main city, which is Addis Ababa. So we have to make it 1 and go to the getRoute function call. So when we get to the getRoute function call, our city, start city has changed. It's going to be Cairo. Our main city also has changed. It's going to be Cairo. Destination is the same, Istanbul. Our current depth is 1 because we've already reached at depth 1. So let's see how getRoute behaves now. All right, so this is going to be Cairo now. We have reached to the next step. This is also going to be Cairo. And our destination is Istanbul, but our remaining depth is 1. So let's search through this again. What we're checking is if our current city is actually equal to our destination city. In this case, we're still not at our destination city yet. So we're going to skip our base case, the first base case here. The second check is actually if our remaining depth is actually 0. In this case, our remaining depth is not 0 because we have still one more depth we want to explore. So what we do here is we go to the recursive part again. In the recursive part, this is where we are exploring for neighbors. If you remember, in the pseudocode version, what we're doing is searching for a link. This also should be a link. Searching for a link between the current city and the next city. But what's the current city? The current city is Cairo here. So this much query is the equivalent of searching, well, find me a link between Cairo and any city you can think of. That's what this much query is basically doing. In this case, our match query is going to be running over our entire graph representation. It starts from Cairo. We don't really care about the link, so it won't look at the flights here, but we start at Cairo and it tries to find our end destination goal. So this is going to be Istanbul 1 and London, the second one. So we have 2 cities that can be reached from Cairo. So our match query is going to return to us 2 cities essentially. These 2 cities are going to be serving like a for loop iteration essentially. So when you loop through a list of cities in another programming language, that is the equivalent of what we're doing here because this match function is going to be returning multiple iterations of cities. So in the first iteration, we're going to check for the intersection of the route so far and the next city. So let me explain this bit of code a little bit. So this intersection atom is a built-in function we have in MeTTa. What it's trying to find is similarities between the route we have discovered so far, the route we have went so far, which arguably should also include Addis Ababa. So this is the route we have discovered so far, but inside Cairo here, that's the city which we started our search for. Our next city, let me write this here. Our next city is going to be two options. The first one is Istanbul. The second one is going to be London. Yeah. So these are our two cities we're basically planning to explore. So once we have those set in mind, what this intersection atom is searching for is this city that we're exploring at the moment part of the route we have already explored so far, because we don't want to repeat the same city in our path, because that will just increase an iteration and a repetition that we don't really care about. So we're basically searching for this, and in this case, to make things more easily understandable, we have Addis Ababa and Cairo in our route so far, and we're going to be checking it with, for example, let's make intersection atom between this and Istanbul, for example. So if our first city is Istanbul, then this intersection is going to be returning nothing, because we really don't have any commonalities between these lists. So that's our clever way of checking if a given city is actually present in the expression of routes we have explored so far. So if that's true, that means we are not repeating ourselves, so we can continue our execution. But if that was true, in case, for example, we have already explored Addis and Cairo, and this match query accidentally returned, for example, say the same city, which is Cairo, then our intersection is going to be returning this Cairo as the common cities between the two expressions, and this equality check is going to be true. It's not going to be true, and we're going to be returning nothing, because we don't really want to keep iterating over the same cities, because that will just lead us in a loop and it won't lead us anywhere. So once we have discovered a new city, in this case it was Istanbul, then our intersection is going to be returning empty. This condition is true. What we do is call another function called union atom. So if any of you guys are remotely familiar with state theory, you probably know what this means. What we're doing is basically concatenating the path we have explored so far, which is Addis and Cairo, that's stored in a list. We're trying to union them with the next city, which is Istanbul. So this will give us a path of Addis Ababa, Cairo, and Istanbul. So we have this path built like so. Apologies. Yes, we have this path built like this. So we're going to pass that in place of the route so far. Remember, the first argument of the getRoute function, you need a recursive call. So the first argument of the getRoute function is going to be this updated route so far we have right here. Then we pass the next city as our current city, because now we've moved from Cairo to the next city, right? The next city is Istanbul in this case. So we've moved from Cairo to the next city, and that next city is going to be Istanbul for the next recursive call. Our destination is the same thing. It's still Istanbul. Our remaining depth is now 0, because we have already explored 1. We have already started with 1, and we subtract 1 from it. Again, if you're having trouble understanding this expression, you just have to put it in the middle, and it basically makes sense. You're basically subtracting 1 from the remaining depth. So when that happens, it's going to be giving us 0. So our next getRoute function is going to have Istanbul here, and as its next city, it's going to have what? The next city is going to be Istanbul as well. Name format is also be to, yeah. So the next city is Istanbul, and our destination is still the same, Istanbul. Our remaining depth is going to be 0. So when we check now our current city and destination, what we're going to check is the condition turned into true, because now we have the same current city and the same destination city. So we will return our route so far. So in this case, this is when finally the function getRoutes return the route it has discovered. So when we finally found the route, we can go back to the first place this getRoute function was called. Well, the first place, this is not actually the first place, we called it here, and this is going to be returning multiple results, and here we're going to be storing one of the multiple results. The first result is Addis, Cairo and Istanbul, we can have multiple results here, remember, because this match query is the equivalent of iterating over multiple cities. So we can also have one of the different cities we discovered before on the slideshow. And this one is going to be from Dubai. We're going to be reaching Istanbul, and there's also going to be multiple other solutions at distance too. So now, here at Search at Depth, we have discovered routes. Whenever we discover routes, we stop recursing anymore because the recursive function, remember, increases the depth by 1. We don't really want to increase the depth by 1 anymore after we found paths because we want the shortest path. So when we reach at this point, if we have already found the found routes. So once that is done, then we go back to the place where the research depth is actually called. Here, we already found routes, and if what we found is not empty, remember, this can still return nothing because if we have no path accessible based on our starting point or based on our depth limits, we might still find empty routes. And if that's the case, we're going to be returning no route. But if that's not the case, if we don't care for multiple results, we can return the first route we found. So this car item is going to be returning the first result it found. But if we also care about multiple results, we can return everything in a single minute. But if you want everything, this is the equivalent of the same function. We can sometimes have a duplicate, so that's why we use this unique item here. We want the unique paths only because we don't really care about repeated paths, so we can return all shortest routes like so. So that's pretty much it, guys. We're almost running out of time, so I would like to stop it here. But feel free to reach us out in the DM. I'll be sharing with you this code so you guys can explore it and play around with it, read through the comments, and try to replicate this on your own. Especially for the next task, it would be a lot easier, a lot. It would be a lot helpful if you guys can try and connect this probably with any kind of front-end application for the Python with the Python integration, just like the demo problem we've been seeing so far, so that you can kind of feel what this would look like as a product when you integrate it. If you also feel a little bit more adventurous, you can also try and integrate some distance into this searching, because we don't really care sometimes on how many stops we make. Sometimes we want genuinely the shortest distance possible, like the shortest amount of time possible, for example. So those are easily representable with a cost you associate with, like I tried to show you at the start of this video. So that's pretty much it from my side. Unless there is anyone who has some kind of question, I would like to hear from you guys. But I would like to encourage you guys to keep playing with this code, try to replicating it on your own, try extending it in your own ideas so that you can better understand what I was trying to explain here. So before we end our today's training, is there anyone with questions? Yes, Francis? Sorry, I cannot hear you if you're talking. Maybe you can change your microphone, or maybe you can write me in the chat. I still can't hear you. Sorry, I couldn't hear what you were saying. Yeah, you can just write your questions in the chat and I can address it from. Remember, everyone, you can also ask any questions in the Telegram and WhatsApp help desk, so that even if after this training, whenever you're trying to explore things and you have questions, you can also ask up there. But yeah, Francis, I would appreciate it if you can write in the chat. I can address your question. Oh, sure, definitely. We'll pin the challenges in the Telegram channel as well. I can also share you right here. Um, yeah, I'll share it here in the chat before we close this meeting. Any more questions from the rest of you? I've shared the link in the chat. I will also pin it in the Telegram and also WhatsApp groups. You guys can attempt these challenges as well. For those of you who've missed any of our previous sessions, you can find them. We'll be uploading recordings online, but until then, you can find some previous contents on YouTube, so you can explore the topics on your own, so that you can catch up with the rest of the group. And yeah, please attempt this challenge because yeah, it's going to be a lot helpful for you and to prepare for the hackathon. All right. So if there is no more question, I think we can end it here. Sorry, what was?
Yeah, well, thank you, Yeb, for your session today. It was really, really very informative, and thank you everyone for joining. Again, I think, just to repeat what Yeb said, if you guys have any questions, we do have a help desk. We have a community if you haven't joined. There's someone there to answer your questions. There's plenty of screen shares on BeyondTheCode.ai's YouTube. Also, 99.9% of these sessions are recorded and shared within our community group. So don't be shy. Look forward to seeing you guys next week. We'll be having some surprises next week on Friday. We'll be awarding individuals for their participation. So I look forward to seeing you guys again on Friday. Have a great rest of your evening or morning, wherever you are. And thanks for participating. Look forward to you guys being a part of the hackathon in September. Thank you again, Yib and Sheila and Rosie, for managing the call. And thank you everyone for participating. I hope you learned something today. I also lastly added that at the end of the hackathon, we are searching for those who actually have learned MeTTa to join our team. These are paid roles. They're going to be supported by SingularityNET. I just got that information today, so it's important. This is why we keep saying we're not here just to hack. We want to find developers that can join us. So keep that in mind and have a great day. Thank you. Bye-bye.